what's it called? The progress, unit progress check, or some more of these problems as well. So, let's take a look. Boom, boom. All right. The thing with heat is that it cannot be created or destroyed, so it must be transferred. There's a few different ways to calculate enthalpies and stuff like this, but there's one major equation to make sure you remember, is that heat equals MS or MC delta T. So if we take a look, 200 milliliter sample of water absorbs 32 kilojoules of heat, specific heat capacity of water. Everything I've seen, you need to have this memorized. What is the change in temperature of the water? So if we take a look, another thing you should have memorized from a while back is that the density of water is 1 gram per milliliter. So 200 milliliters of it is 200 grams. So that's the mass. We have 32 kilojoules. Since this is in joules, we'll want to change this to 32,000 joules. And this is our C or S. We are looking for delta T. So if Q equals MS delta T, this is page 8, problem number 4, by the way. We want to take and find delta T. We have MS on each side. So 32,000 joules over 200 grams and 4.184 joules per grams degrees Celsius. You can see my grams and joules are going to cancel out. That's going to give me 1 over degrees Celsius, which is the inverse of the inverse. So that gives us degrees Celsius. 32,000 divided by 200 divided by 4.184.
The answer is about 38.2409.
2 significant digits there, so 38 degrees Celsius. To make sure that she heard me correctly. So that is the change in temperature. Trying to think if there's anything else you need to remember for that. Change the kilojoules to joules. Nope. Mass. A lot of times too, whenever you have solutions, like let's say you have something dissolved in water, they will use the specific heat capacity of that solution as the same as water. And most of the time it will tell you that, but don't freak out if if you see like it mixes two things together. It will also sometimes just tell you to use the density of water for that as well, even though it's a solution that may be a little more massive than water per milliliter. So that's the change in temperature. It says, what will the final temperature be if the water above's original temperature was 19 degrees? Well, the thing is we need to see if it was absorbing or losing that amount of energy. It looks like it was absorbing it. So if its original temperature was 19 degrees, that means the change is positive. So 19 plus 38. What do we get there? 57? 49, yep. 57 degrees Celsius. So that is a simple Q equals MS delta T problem. Same thing here. More of the same practice. So if we take a look, this is very common as well. We have some type of metal. This is page 10, question number 9. So we have some type of metal, or maybe you have 2 different amounts of water. It's really nice if you have 2 different amounts of water because the specific heat capacity is going to cancel out right away. But basically, we need to find this Q and compare it to make it equal to the other Q. So we have a piece of metal. initially at 100, dropped into 244 grams of water at 10 degrees Celsius. The final temperature when it comes to equilibrium or thermal equilibrium is 15.3. What is the specific heat capacity of the metal? So again, you can set Q equal to negative Q on this. But the fact that we're not having to solve for final temperature, we can solve for the Q of the water and compare it to the Q of the metal. Either way you want. So we have the mass of the water here. The change in temperature of the water is 5.3 degrees Celsius, 4.184 joules per gram degrees Celsius, and then the mass here, 244 grams. (244) times 4.184 times 5.3.
The answer is 5,410.748.
So that is in joules. So that's how much energy the water has gained. So if we want, we can sit there and say, okay, that's negative. And we can set that equal to the energy that the molybdenum has lost. So final temperature minus initial, 15.3 minus 100.
It's negative 84.7.
So right there, if you're questioning that negative sign, why I've done that, it's because this is lost energy. So the final minus initial will be negative there. And then we will cancel that out. That's degrees Celsius. The mass is 237 grams. And the specific heat capacity of the molybdenum, we don't know. 237 times negative 84.7.
The answer is negative 20,073.9.
So we'll divide both sides by negative 20,073.9. And that will cancel that out. And these two. And we get the grams times degrees Celsius on the bottom over here. 5,410 divided by 20,073.9. The negatives will cancel
That would
out.
be about 0.2695.
0.2695, three significant digits with the 244. 0.2695 becomes 0.270 joules per gram degrees Celsius. Again, if you were solving for final temperature, you have to set the whole problem up as one thing because both sides have that variable of final temperature. Heating and cooling curves. So you need to know that the delta H of fusion is the amount of energy required for freezing. You remove that energy to freeze, or you insert that energy to melt. We have it in joules per gram. Keep in mind that that could easily be given to you in joules per mole or kilojoules per mole. Same thing with the heat of vaporization. And that's another thing. Like there's going to be a lot of these delta H's. There's like, they can put C there, which means combustion, fusion. You basically have to just look at what you're specifically doing. They can say a reaction, a formation, all of those different delta H's. The cool thing is it's just energy. It's enthalpy, you know? So whatever it is you're doing, you should be able to find a way to use that delta H to use it like you want. So let's take a look at what we have here. Is added to 1,000 grams of ice. All right, that's a fun one. So 4,000 kilojoules of energy is added to 1,000 grams of ice at 0 degrees Celsius. What is the final temperature of the water? The first thing we need to do is to figure out if we can actually melt this 1,000 grams of ice. If we can't, the final temperature will be 0. So let's take, and we have 1,000 grams of ice. It takes 333 joules per gram. Oh, how did I put that on bottom? Every 1 gram takes 333 joules. So that equals 333,000 joules, which is 333 kilojoules. We then have 400 kilojoules we know of. If we subtract that 333, we get 67 kilojoules. So that's the amount of energy we have to change the temperature of the water from 0 degrees up to wherever it goes. So if we take a look, we know the initial temperature is 0. The T of F is what we're looking for. We know that 4.184 joules per grams degrees Celsius is the specific heat capacity of water. And we know that we have 1,000 grams of this stuff. And we have 67,000 joules. So if we multiply the 1,000 by 4.184, we get 4,184. We're going to divide both sides by that, 4,184. 67,000 divided by 4,184. T of F minus 0 is obviously T of F. So T of F equals 16.0. A lot of garbage digits here. So, you know, I would probably put 20, but 16 works, degrees Celsius. I don't think this problem was set up for significant digits to worry about it. It's at 0. We've got about 400 kilojoules, right? Questions there? All right. Bunch of the same stuff. Page 17. So what I've done is I've given you the enthalpies of the reaction first, so that basically you understand that that's for the whole reaction, and you can use that in many different ways. If you're given moles, you're given grams or whatnot. But if you take a look here, this is all those delta H's that I was talking about. We've already done delta H of vaporization, delta H of fusion. Heat of the reaction. I mean, a reaction could be a combustion reaction, so that's the same thing as delta H of combustion. You have all of these different, if it's an acid-base reaction, then that's a delta H of neutralization is the same thing as that heat of the reaction. So just keep in mind that it all works the same. So if we take a look, N2 yields, N2 plus 3H2 yields 2 ammonia. The delta H of the reaction is negative 92.6 kilojoules. Is that endothermic or exothermic? Anybody? Exo. How many grams of N2 are needed to make negative 550 kilojoules or release 550 kilojoules? So this is the delta H of the reaction. We want 550 kilojoules. Every 92.6 kilojoules released required 1 mole of N2. And every 1 mole of N2 is 28.02 grams of N2. Negative 550 divided by negative 92.6 times 28.02.
It's about 166.4254.
So we need 166.4, it looks like, grams of nitrogen. Heat of formation. A lot of these, if you recall, goes products minus reactants. You need these standard heats of formation. Remember that anything that's in its elemental form will be 0. So if we take a look, if we're doing this problem right here, this would be 0 and this would be 0. Both of these are in their state of matter. If this specifically said that it was diamond, then we might need to look further into it. Remember that these enthalpies, these heat of formations are standard molar enthalpies. So it is kilojoules per mole used. So there we had silicon dioxide and carbon dioxide, or carbon monoxide. Carbon monoxide. So we take the products. CO is negative 110.5 kilojoules per mole. And we subtract the reactants, 1 mole of this. We have negative 859.4. So that's 221. Negative 221 minus negative 859.4. Negative 221 minus negative 859.4.
It's 638.4.
We get 638.4. When you take sand and react it with carbon to get silicon and carbon monoxide, if we take a look, that positive means that we need to put energy into it. It is endothermic. Using those standard enthalpies of formation, you might be able to calculate these heat of reactions, or they just give them to you. Remember, if we were to have A get to D, that is one path. But for heat, if we can take A to B and B to C and then finally get to D, the amount of energy here for A to D is equal to the amount of energy of A to B plus the amount of energy to B to C, and then finally the amount of energy from C to D. So if we add all these up, this is the same. Doesn't matter the pathway we take. So we have calcium on this side. We're going to use Hess's law here. Calcium is a reactant here as well. We have 1 mole of each. So that's pretty good. I picked the easiest example ever. I did, didn't I? So if we take a look here, we have 2 moles of water on the reactant side. From here, though, we have 2 moles of water on the product side. So we are going to have to flip this reaction. And if we take a look, if we flip that, that means that we need to change the sign there from negative to positive. And with multiple reactions there, my head starts reading everything every which way. So I have to usually cross things out. So if we take a look here, here I have O2 on the reactant side, here I have O2 on the product side. So that cancels. Here I have H2 on the reactant side, and I have 2H2 on the product side. So one of those cancel, and we're left with calcium plus 2H2O yields calcium hydroxide plus H2. So that looks good. Since this matches our heat, our reaction that we want to get, that means that this down here is the A to D, and this up here, if we take a look, here's a different pathway. So basically, we need to just add these two together. Negative 986.6 plus 483.7.
It's negative 502.9.
So the delta H for that equals negative 502.9 kilojoules per mole of calcium. If we did this and then they say, well, how much energy would you be able to, or how many grams of water would it take to get 2,500 or something like that? Then keep in mind, we can now use this. And we know every 2 moles of water is going to, that's used, is going to be able to emit this. And that's the way a lot of those free response questions will be like. You find one thing first, and then you use that to basically find something else. Just keep in mind, once we got that, then we can use it to find any situation. The one big trick with this is that you have to remember that it takes energy to break bonds, and energy is released when they reform. Did you do the multiple choice one, or did you just start with the free response one? Yeah. One of the things they do is they try to mess up the words on, like, the words on this kind of get weird. Like the bonds broken has more energy than the bonds released when they formed or whatnot. They sit there and they talk about that in there. So you have to be pretty, you have to read through it maybe a few times. But basically, we're going to figure out the energy of the bonds broken, and we're the energy needed to put into it for the bonds to be broken, and then we're going to subtract that from the energy that's released when the bonds are formed. So use the bond energy given to determine delta H for the reaction. Keep in mind again that all of these are per mole. So if we take a look, we have N2 here. We need to make sure that we understand that N2 is a triple nitrogen bond. So if we take a look here, NN, that's not going to do it. We need to be more careful. Down here, it's 942. We have 1 mole. So that is bonds that are going to be broken, 942 kilojoules per mole. We have 3 hydrogen. So if we take a look, 3 moles of hydrogen, that is 1 single bond, that's 432 kilojoules per mole each. We're going to sum the energy required to break all these bonds up, and then we are going to subtract the energy that's released whenever the bonds are reformed for ammonia. So ammonia, what type of geometry do we have with ammonia? Three bonds, 1 unshared pair. Nobody. Good. Good. Trigonal pyramidal. Good. So we have 1, 2, 3 hydrogen nitrogen bonds. For each mole of this, we have 2 moles of this. So 2 times 3 is 6. And every nitrogen hydrogen bond is 386. Three times 432.
That would be 1,296.
6 times 386.
It's 216.
6 times 386.
It's 2,316.
942 plus, I can't read my own writing, 3 times 432.
That would be 1,200.
There we go. 942 plus 1,296 minus 2,316.
Sorry, I can only call one.
That must have looked like a phone number to her. 942 plus 1,296.
That would be 2,238.
2,238 minus 2,360.
It's negative 78.
Negative 78 kilojoules per mole. And keep in mind, that is the delta H of this reaction now. All of those delta H's of those reactions, there's different ways to find them. So if we wanted to now, we have the delta H of this reaction equals negative 78 kilojoules per mole. If they say, well, how much energy will be released if we make such and such a grams of ammonia, then that's what we would do. We would sit there and use this from the grams of ammonia to moles of ammonia to kilojoules. Boom. Dun, 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 dun. These are some previous AP questions just to show you like how some of them are made. This is what we're going to go over tomorrow. But if we take a look, this one's kind of interesting if you want to try this one this evening. We've got C2H5Cl plus Cl2. So C2 H5Cl plus Cl2 yields C2 1, 2, 3, 4. C2H4Cl2. Let me switch this. I want you to be able to see this maybe a little bit easier. Let's keep it as similar to that as I can. Plus HCl. Now, in reality, you can look at these two things and say, okay, we're breaking that bond and we're breaking that bond. And you can find the summation of just the bonds broken there. And then you could subtract the summation of the bonds reformed here. If you can see what has actually occurred in the reaction, you don't have to sit there and break all the bonds and reform all the bonds. Does that make sense? Yeah. Does that make sense at home? Since this is the only bond being broken here and the only bond being broken here, if we add those up and then we subtract the energy released from the reformation of these bonds, we can actually do this problem without sitting there going, okay, I've got 5 CH bonds. Now, can you do it with I've got 5 CH bond way? Yes, because whenever you do that, you still have, 4 CH bonds over here. So it will all work out either way you do it. That's something that is totally up to you. This is like one of the ugliest ones that I came across. Basically, they give you this and then they give you this, and it's they're just trying to code things. The problem with this type of thing is that if you look, we have 1B here, we have 3 B's here. So we don't actually have, this is page 24, we don't actually have the mole, it's not balanced. So the first thing you would have to do would be to balance all of this. Same thing down here. They're basically showing you that if we don't want you to have to draw something out, then, or we may give it to you, but then you would definitely still have to balance this. For something like this, I don't think that you guys have the mechanisms to sit there and figure out like which bonds are necessarily breaking and reforming. So it might be easier that after you get all this balanced, break everything down and then reform everything. But yeah, that's like that would be like, you know, first semester college organic chemistry. This type of thing right here, yeah, I would dread that one, but I will show you how to do that one tomorrow, as well as this right here and this right here. And that will put an end to our thermodynamics unit for a while. If you've been using the AP classroom, you'll notice that thermodynamics comes back. Tomorrow we'll also talk, one thing that they do in that second part of the unit is they talk about entropy. And I don't know if you guys have ever talked about entropy before. I probably didn't mention it last year because it would have been done after we were already in quarantine. But entropy, S is entropy. And entropy is disorder. Basically, the universe tends to go to disorder. How many of you have a junk drawer at home? Yeah, right. You get some drawer where you throw everything. Or how does your bed look? Or how does your desk look as it sits there? Things tend to go to disorder. Well, what does that mean? Well, if you want to clean up this desk, you've got to put energy into it, right? And that's how basically we'll look at how energy and entropy fuel forward reaction. But the cool thing is, if you're going to try these tonight, delta, actually, I don't want a delta sign. Yeah, I do. Delta S equals the summation of the products, the entropy of the products, minus the summation of the entropy of the reactants. So if you take the entropy of all the products and you figure out how disordered they are, you subtract how disordered the reactants were, you can find the change in entropy. If the change in entropy is positive, it's going toward more disorder, which is actually favored for in the universe. If the entropy is negative, it's somehow gotten more organized. But other than that, I think that's going to do it for me today. Have a great day. I did record this. Did he make it up? He did not make it awake. That's funny. Have a great day, guys. See ya. If you have any questions, obviously, you can stay on. Oh, Hayden. Oh, he's gone.